Uncertainties are among the most significant factors that affect the future performance outcomes of engineering systems. Engineering systems are often, if not always, design, manage and operate under uncertain circumstances, such as shifting needs of customers, changing demands, and evolving technologies. Uncertainty has downside, like unexpected breakdown in power facilities, but also provide upside opportunities like higher electricity demand than expected. Both sides of uncertainty will affect system performance greatly. As a decision maker, you need to think carefully about how to deal with these uncertainties. The power grids are continuously exposed to numerous sources of uncertainties which threaten the reliable and secure supply of electricity. The demands for a power grid are highly uncertain due to weather and other conditions. Meanwhile, high penetration of renewable generation, such as wind, triggers volatile supply. For instance, the peak power output of Germany's wind farm was 200 times higher than its minimum output in 2013. All these factors bring great challenges in grid management and generation scheduling to power system operators. One way to deal with uncertainty is to make prediction. However, forecast can be severely wrong due to the fact that most of infrastructures have a long lifetime, usually for 10 years, 20 years or even longer. And they will undergo many variations. If we use too many assumptions, especially too optimistic ones, the results will be very surprise and usually bad surprises. A better approach is to recognize uncertainty a priori before the project is designed. We should explicitly consider that the forecasts we use for our design are really ranges, so the possible outcome is also a range. Flexibility should be played into design and management. That is, we should design ways to adapt to the future when we know about future price, demand and other things like that. Flexibility, also referred to as real options, provides the right, but not the obligation, to change the system in the face of uncertainty. Real options are embedded choices in a project that can be exercised when circumstances turn out favorable, or can be ignored when exercising such choices will not improve performance. We should think of designs that make the outcome distribution better, rather than optimizing for a single point estimate. Graphically, if we have a cumulative probability distribution of the net present value for the original fixed design, flexibility is able to cut downside risks and expand the upside potential, thus shifting the distribution to right-hand side. To embedding flexibility in power grid systems, one way is to phase the deployment of power capacity. A phasing strategy is the breaking of system development into sequential phases, rather than building it all at once. Committing your budget to early investment in the game may seem appealing, as the resources you bought can be used for a longer period of time. However, the commitment value created by investing early may be reduced by uncertainties as demand patterns change over time. By delaying your investment or phasing the investment to mitigate, you can mitigate the risk of wasting capacity due to overestimating the demand, and risk of demand pattern shift considering a long-term horizon. To apply real options or flexible strategies in power grid system, you should know when it is appropriate to exercise them in operations. A decision rule is a triggering mechanism that designers and operators can use to decide when it is appropriate to exercise the flexibility. It aims to simulate an appropriate decision taken by the system operator or manager at any given point in time to adapt the system to changing conditions. Such rule is typically based on the observation of a given uncertainty source like demand generator outputs to which the system is called to react. The decision triggers for exercising flexibility in the system regarding new generator installations and capacity expansion are formulated as if statement. In this game, the underlying uncertainty lies in generator outputs. Suppose you know the range of variation of the output of every generator in every time period, thereby also knowing the range of the total output over all generators in every time period. The phasing decision rule is that if the total output over all generators available falls in a certain range, then a fixed set of setup decisions will be taken. For instance, in period 1, the expected sum of total output over 5 generators is 1615, which falls in the ranges between 1598 and 1773. The decision is to set up a new PC generator in this period. For wind generator, the decision is not to build any new wind generator. All these phasing decision rules are predetermined and fixed. When the total output over all generators falls in a certain range, a corresponding decision rule is determined to make sure that the power grid can provide enough power to meet the demand under different circumstances, while minimize the overall cost.